So today I want to take a look at the a monad transformer for the either data type. We did option T last time, and so we'll do similar type examples, but I kind of want to just look at transformers again in general. Probably next time we'll move on to start looking at some specific data types like the reader monad or maybe some others. But anyway, so I have a similar project to what we used last time. I have structures on my class path, very simple build.sbt. So we have structures on our class path, and I have an empty source file or project here. And the way I want to start today is by creating, we'll create a file called EitherT.Scala. And we're going to put this in the transformers package. And so it's been a while since we looked at option T, but if you recall, we created a case class for option T, and we wrapped a value of a specific type. Here, the value, basically was an option inside of a type constructor. And so here we're going to do the same, but we're going to put it inside of an either. So basically, the value we're going to wrap is going to have type of f either, and then we're going to take two more parameters, L and R. So I've used three parameters here, f, L, and R. We're going to have to take those as type arguments on our EitherT type. F is going to be higher kinded, and then we'll take the left and right types explicitly. And this pattern, this idea that transformers let us work on, like the EitherT transformer lets us work on some arbitrary f that has an either inside of it. That notion is pretty important, but like in general, when we're working with monad transformers, it's always good to find like the value that it's wrapping. So for example, I want to jump to the REPL for a second and like look at Scala Z. We can just pick like a random transformer type. So let's pick like state T, for instance. So we've got some pretty gnarly type here. It's like index state T, and it takes this one higher kinded type parameter. It takes three more type parameters. And if we kind of bounce around this code a bit and try to search for what value it's wrapping, we should be able to find something pretty straightforwardly. And so here, this particular type, it happens to be in this apply method. You can see that given a value here of some crazy shape, like a function S1, that when applied with an S1, returns like an f of a tuple, of S2 comma A, like whatever that is, I don't know. But the point is that apply lifts one of these shape values directly into this index state T data type. And this is a pattern, we can apply over and over again to various transformers we work with. So for example, if we looked at like the Scala Z version of EitherT, it ends up being quite a bit simpler to find the value it wraps. It ends up being very similar to the one we're about to define. You can see it, this one's defined as a case class rather than as a trait with an apply method. We've got this run value, which is an f of A or B. So again, like, anytime you're working with a transformer, the name, might not necessarily be that useful, right? EitherT doesn't really tell you much about what it does, but instead, just use this idea of trying to find the value it's wrapping, and that'll give you an idea of like what this thing lets you work with. Okay, so, back to writing our own EitherT. We have something that looks very similar. We're going to wrap an f of either L comma R. We're going to use the Scala standard libraries either here, rather than using like the Scala Z disjunction. And now what we want to do is start defining instances and convenience functions for working with this thing. That lets us, for instance, treat it as a monad or treat it as a functor or whatever. So let's just start with the empty case class definition, and we'll write an instance for functor in the companion object. So we'll do something like this. We'll say, we'll define an implicit val. We can just call it functor instance. And now remember, functor is defined on a type constructor of one argument. EitherT clearly doesn't fit that shape, right? Because we've got 3 arguments. The first is higher kinded. So we need to fix like f and l here, and we're going to have we're going to let r vary, and then we want to create an instance of this. But let's just hold off on that for a second. So anyway, this is what we want to define. We need some imports in order to be able to do that. First, we're going to have to import structures. So that's going to give us our definition of functor. And now the next problem is that our build.spt was a little too simple. Well, there's a couple of different problems here. The first problem here is that we're using these types f and l that we haven't declared anywhere. Remember, we did a very similar transformation when we defined option t. We basically need to take those as arguments to this function. And of course, in order to do that, we're going to have to change this val to a def. The next problem we have, though, is that we just are using this syntax that, remember, we get from the kind projector Scala compiler plugin. We don't have that configured in SBT right now, so Scala is just telling us that it doesn't know what this question mark is. So let's fix that in our build script. And we'll actually just take it from like the structures build. And just paste it into here.
Is that something that all our internal Scala functions are built with?
No, not right now. Probably should be, but yeah, not currently at least. Yeah. Okay, so we can see we're compiling now. So let's get out of our build scripts and go back to our code. So this functor instance, we've got the type signature right. We now actually have to write out the implementation. So we're just going to steal this definition. We can just save. We'll let the compiler tell us what we're missing. And it says, oh, well, we're missing this map method, right? That has to have this particular signature. So let's define our map function here. So remember, map basically had this signature that said, given an f of a and given a function from a to b, we could return an f of b, where f in this case was like the functor type we're dealing with. So let's substitute in, our functor type here, this big shape. And what we end up with is EitherT of f comma l comma a has to be mapped to an EitherT of f comma l comma b. So we'll just leave that undefined for a minute. You can see we got successful compile. And when we define the option implementation of map, we were able to define, eventually what we did is we moved some of those functions directly to option t. So let's just do that now. Let's define map directly up here. We'll say map, the instance method map on EitherT will be defined to take a function from the right value to some other type s. And if you call that, we'll give you back an EitherT of f comma l comma s. So we'll come back and fill that in a minute. But now, given that implementation, we can trivially implement the one here on line 15. We'll just say fa.map f. Okay, so now let's implement map up here on the case class itself. We have this value. It's an f of either L comma R. Basically, what we're going to need in order to be able to implement this map is some way to map over the f type. Like if we can get inside to that either value, then we can easily map over the right side of the either. So the question is basically, if we can somehow first get the inner either, we'll just call it E for a moment. Then we could, let's say, create E2 of type either of L comma S just by saying E.write.map F. And this is like weird Scala either API, right? That you have to tell it what side of the either you want to map the function over. But nonetheless, we get back an either here. So first we have to have some way of getting this E out of our value, and then we have to have some way of putting one of those things back into the F type constructor, and then wrapping it with EitherT. And so anyway, this sort of looks like a normal map call. So if we were to ask for an additional parameter here, right? If we were asked for like a functor definition for F, then we could just map over our value and work directly on our either. So what I mean by that is by defining this value, this implicit parameter F, which is of type functor F, that lets us do f.map value. And now here we get our either type E, right? In fact, I'll just write this out this way. And so since we have E, we can just delete that. And now we've got this value, E2. And in fact, we can delete this because we just want to return the result of this expression directly. So we'll just delete that type, or that val declaration, and we're left with this. The only problem with this is that mapping over an f of either L comma R, we're going to get back an f of either L comma S. But what we need to return overall is an EitherT. So let's save and see the error we get. We should see that. It's, you know, we're basically getting that. It's saying that it found this f of this crazy inferred type, serializable with product with either L comma S, and it required an EitherT. So we just want to wrap this this type here with the EitherT case class. And type inference takes care of the rest. That serializable with product ended up just going away. That was just you know, the least upper bound being calculated a little too strictly for our taste. But nonetheless, you know, type inference is able to say, oh, okay, you want to wrap this into an EitherT, and it's able to figure out that we don't really want it to infer that product with serializable nonsense. And anyway, that part compiles. Unfortunately, we still have this other compile error, which is down here in our functor instance for EitherT. And it's saying, well, wait a minute. In order to call map now on our instance method, you need to have an implicit functor in scope. So because of the way we've defined this functor instance, we can just delegate that requirement directly to the implicit parameter list of this implicit def. So we can just say, in order to get a functor instance for an EitherT, you have to give us a functor instance for f. And so if we save, everything's now compiling. Okay, so let's try to use this for a moment, and then we'll come back and implement something a little more exciting. So let's start with some value called x. And let's say it's a list of either strings or ints. So this type, x, has the appropriate shape such that we could wrap it with EitherT. So if we said like import transformers, because we've got an either inside of some type constructor f, we should be able to say EitherT x. And I will call this like xt. And in this case, it worked out okay. Scala was able, or Scala C was able to infer the types of f, l, and r. Right? Like all we did was just said EitherT. We didn't tell it the type parameters here. And it was able to figure out that the outer type constructor was a list, and the left value was a string, and the right was an int. Okay, and then of course, all we've defined is like the map function, so we can say things like map, +1 over it. Let's see here. Okay, so we could say that, but what it's complaining about is that it can't find a functor for list. So let's import our standard definitions from structures. I think we've defined them here. Okay, so we imported all of our standard type class instances. So now we had a functor for list, and as a result, we can call map on xt. And you can see inside here, where there was a right, the value was incremented, and where there was a left, it was ignored. Okay. Because we have a functor instance, we can actually just request a functor of EitherT list string question mark. Right? Because a functor, of course, it has to be a single parameter type constructor. Well, we could do that if we had it imported. Right, and we get this functor instance res3. Why would we want a functor instance if we can call map directly on the value? Right, and it's for the same reasons that we've talked about before. One is that code that's written generically to work on any functor can now work on EitherTs for free. And two is that we can compose these functor instances with others. So for example, we could say res3 compose with, let's say, the functor for, let's make it easy. Let's just say another list. And what we have as a result is some pretty complicated type, but that handles a list of eithers where the left value is a string and the right value is a list of x's. And yet we can still map over that. So like that's a weird type, right? But let's write an example out. So we have here a list of eithers. First we'll do a left value as a string, or where the right value is a list of ints. Okay, and then another right value is going to be list 4, 5, 6. So we have this weird type. And now what we could do is say like res4 map over the wrapped version of this weird value. And we'll map like the increment function. Type inference starts to fall down a little bit at this point. And this is very common when working with transformers in Scala C, because we're relying on Scala C to be able to infer, like, for a given value, what's the f, and in our case, what was the l and what's the r. So we're going to have to help it along. First, let's try to just use EitherT with the weird value. And we get an error, just that. And it says that what it found was a list of product with serializable with either. So first of all, like we have this weird type inference happening again, where like the Scala C is inferring a more specific type than we really intended. So first, let's try to fix that. We'll call it weird2, and we'll just explicitly annotate that we have a list of either a string or a list of int. Right? That's all we did when we created weird. So we can just define it like this. Right? So if we ask for like the type of weird, we get back that. If we ask for the type of weird2, we just get rid of that extra product with serializable stuff. All right, so that's one step. So now let's see how EitherT weird2 works. In this case, Scala C was able to do all the inference, and we were able to lift that directly into EitherT. Sometimes we don't get that lucky, and we might have to write something out like EitherT of list, comma string, comma list int, and be really explicit about it, and then pass weird2. Well, I spelled it wrong, but that would have worked fine just as well.
Is there a way to bypass what you did with declaring weird and then declaring weird2? You just explicitly somehow declare weird in a way that's resolvable?
Yes. So let me scroll up. So here's how we defined weird, right? We just said like list of left and right. So one way to avoid this, let's define weird again, actually, all the way down here. That's weird scroll off. But basically what's happening is that because we didn't provide a type for the weird val, then Scala C tried to infer a type by looking at the right-hand side, and it inferred it as that. So one way to avoid this completely is to just be explicit in the type of the val. So basically, rather than relying on inferenced right here, we would just say list of either, string, comma, int. And then, well, sorry, same thing, right? But I actually don't use the wrong type. List of int here.
So that's normally what you would want to do when you're declaring something like that.
Typically, yeah. I mean,
right.
Yeah, if it's only, like a local val that doesn't escape like very large scope.
The inference is obvious.
Right. Exactly.
It's complex.
Yeah. And I will point out that like this weird inferencing that's occurring where we're getting this product with serializable type. I mean, pretty much if you ever see product with serializable, it's an inference problem. You got to think about it. But this is completely avoidable. There are ways to make it so Scala C, when designing a library, doesn't, infer that wacky type, which I'll show you that in a second. But since, either's in the standard library and it didn't follow those kind of guidelines, we're kind of stuck here. Okay, so let's put all these pieces together and say we've got a functor now for EitherT of list, comma, string, comma, question mark, right? And we're going to compose that with the functor for list. So that's going to be res9. Now with res9, we can call map over weird using the increment function. And we're almost there. I forgot to wrap weird in EitherT. Right? And like this is all very common type, the types of mistakes people generally are making in Scala when using transformers. Like in this case, we just forgot to use the transformer. All these things are pretty typical. So here we're trying to map over the wrapped version of weird. And finally, we were able to increment. And so anyway, what you should see is like 2, 3, 4, and 5, 6, 7, right? But all the lefts have been ignored. And again, like this functor composition works with any functor. So if you've got like a functor for future or something that's actually like a little more interesting than just a list or an option, the same exact pattern applies. Okay, so let's take a diversion into library design. Let's define Actually, let's, yeah, I suppose we can do it at the REPL. So what I want to do is define a very simple abstract data type. So we'll define a sealed trait. Let's call it widget. And we're going to give like 2 case classes that derive from widget, right? So we'll have case class sprocket. And we'll have another case class, woozle extend widget. Okay, so very simple abstract data type here. So watch what happens if we say, let's define x as the list of sprocket 1, sprocket 2. Type inference kicks in and figures out we've got a list of sprockets. And if we do the same thing with woozle, inference works fine and tells us we've got a list of woozles. So let's try sprocket 1 with woozle high. And we get product with serializable with widget. Right, so this is the same case as like we have either, we have left and right, and we get this really specific type. So what's actually occurring here? Well, all we've told Scala C about widget right here is that it's a sealed trait, and it happens to have 0 parameters, but that doesn't, I mean, 0 methods, 0 members, no types, no methods, no vals. But it ends up, having methods doesn't actually help us all at all in this case. The point is that the type itself, there's nothing about it short of the fact that it's going to extend from any, right? Or really, it's going to extend from any ref in this case, because by default, traits extend from any ref if you don't specify it. Okay, but what about case class? When we define a case class, we get a whole bunch of stuff, right? Let's try this. I think this should be easy. If we use Java reflection to reflect over sprocket, let's see how hard this would be. Well, I'm forgetting my Java reflection API. But basically, if we reflected over all of the super types of sprocket, we would see that it doesn't extend just woozle. It certainly extends woozle because we told it to up here. Or sorry, widget. Right here, we said extends widget. But by nature of being a case class, it also extends serializable, and it extends product. So for example, what we could do is say val p product equals sprocket 1. And that's completely legitimate because all case classes extend from the product interface, or trait in this case. If we were to look in Dash, like, well, what the heck is product? For the record, I actually am licensed for Dash, but I haven't copied my license to this machine yet. If we look at product here, you can see it's got a bunch of methods like product arity, and we can iterate over all the fields, right? So we could say like p.product iterator .toList, for instance. We get back a list of all the individual fields of the case class. But it ends up not being very useful because it gives us like a list of any. And like, since we're talking about parametricity and using the features of the type system, there's not much we can do with a list of any. All we can do is ask for its list, unless we start cheating and downcasting and doing runtime type checks and whatnot. Okay, so anyway, the point is that all case classes have both product and serializable by default. Extend serializable, and I can show you that just by saying s serializable, and that compiles fine as well. So anyway, when we've got like a list of a sprocket and a woozle, Scala C has to find the least upper bound of those two types. So if you looked at like all of the super types of Sprocket and Woozle, it's going to find the most specific type that's a parent of both of them, right? And it has to be that. It has to be the least upper bound, because if it was like the most general type as a parent of both of them, then it would always compute any all the time, right? So you always want the least upper bound. And in this case, the least upper bound is much more specific than just widget, right? It's like, well, both of these are widgets, but they both also are products, and they're both also serializable. So we get this wacky type. Okay, so anyway, how can we fix this? Is this just like a fact of life due to Scala's least upper bound calculations? And the answer is no. There's a beautiful trick. It's a very simple trick, like from the nicest kind, right? Nothing fancy at all. The idea is that can we just require widget to be product with serializable? So we're going to take this same example, and we're going to paste it again. But on widget, we're going to say extends serializable with product. And that's it. So we're going to say that widgets now, in addition to being any refs, also have to be serializable, and they also have to be products. And that's generally okay. Like when you're designing abstract data types, that generally doesn't hurt. Generally. Oh, it didn't actually paste. Let me try it again. There we go. And now if we can basically say val z equals list of sprocket 1 and Woozle h, and it infers list of widget, right? Because they still both have serializable and product, but since widget also extends serializable and product, it ends up being more specific than the general type. So this is a really neat trick. You will see this all the time, but like this is pretty advanced Scala library design type concern. It's very frequent when people see a library and it's like, hey, why do you have this weird extend serializable with product? If you see that, this is exactly what they're doing. It's always to work around this type inference issue. Okay. All right, so let's go back to our definition of EitherT here. Let's define just one more. We'll give it this data type a monad instance as well. So let's say monad instance. We're going to require F and L again, right? We're going to leave the implicit parameter off for a minute because we want to be guided into adding just the bare minimum that we need to implement this. And say that we're going to return a monad for EitherT FL question mark. Remember, there are two functions we're going to need to define for monad. We're going to have to define pure. What we need to return here is going to be an EitherT of F, L, A. We only have one way to construct an EitherT, right? And that is to wrap an F of L or A in this case. So we're going to somehow need some expression here which has type F of L. That has type F of either L, A. Well, we can easily, to lift this A value, we saw when we did the either data type that really what we're trying to do is put it on the right side. We're going to make either be right biased. We want all the good values on the right side. We can easily create an either with the A on the right side, no problem, just by saying, right of A. Somehow you now have to get that right of A inside of an F type constructor. In order to do that, we can say f.pure. That should be good enough. Now, a couple things, though. One is that we don't have even an f value at this point. So we're going to have to add an implicit parameter to this function in order to be able to call pure on it. The bare minimum, let's just do bare minimums for the time being. The bare minimum type class that defines pure is applicative. So for now, let's just start by saying, since all we need is pure, we're going to define f to be of type applicative. Okay, now that will be all we need for pure. And looks like Scala C was able to infer all the types okay in this case, so everything's fine. Now we have to define flat map. So let's do that. All right, so flat map, we have an f of a. And so using our same trick of substituting in, we're going to get f of l comma a. And now we have this function f, which is going to go from a to either t f of l, fl b. B is going to be a parameter here. And overall, we're going to have to return either t of f comma l comma b. Let's make sure we got the signature right. We'll just save, let it compile. We did get the signature right. This is a bug actually in Simulacrum, in the current version of Simulacrum. So we're going to have to temporarily put Simulacrum on our class path. Basically, what the error is saying is that as soon as we pulled Monad in, it ran into a problem because Monad has a simulacrum annotation in the class file. That's the bug. Simulacrum annotations aren't supposed to be stored in class files. But anyway, we don't have simulacrum on our class path, so it's complaining. So we're just going to drop in this stuff from the Simulacrum web page, which adds Simulacrum to our class path. All right, so now this should compile, or it should give us a different error depending on whether we got it right. But either way, we shouldn't get that wall of text about a bad annotation. All right, so everything's compiling. So we got the signature right for flat map. Now we just have to fill it in, and we're going to do the same trick we did earlier. What we want to do is say fa.flatmap f. We haven't defined a flat map method on EitherT, and I'd like to define it up there to make this class easier to work with. So we'll put flat map up here. And I'll do a similar pattern for the names here. Given an r value, we're going to convert that to an EitherT value of f comma l comma r. And you end up getting back, oh, sorry, that should have been f comma l comma s. And of course, you get back an EitherT of f comma l comma s. Now we're going to have to implement that. And we're going to end up implementing it in much the same way we did above. We're going to call f.flatmap. So we're going to require, at the very least, we're going to require a type class that has flatmap for f. And we'll do that in a second. But so we're going to call f.flatmap. We're going to start with our value that we have here. So then what we get inside here is going to be e. And that's going to, of course, have type either l comma r. And now, because we're calling flatmap, we know that whatever we put here has to be an f of something. Can be an f of anything. It could be an f of int, right? But that's got to be an f of something. If we do that, then overall, like let's say we return like some random value. I'll call it question mark x. Then overall, what we're going to get back here is an f of question mark x. Now we know we're going to want to wrap this whole thing in EitherT, just like we did with map. Right, so I'm going through this reasoning pretty fast, but if we know we have to wrap all this in EitherT, and we know we have to return an EitherT of FLS, if you work through it, what that requires is that it forces our x type here to be an f of either L comma S. Right, just using normal algebra, nothing fancy. It's working through all those constraints. Okay, so we've got an either of L comma R. We have to return an f of either L comma S. Let's look at what we have here. Well, we have an R. We have a function that takes an R as input and returns an EitherT of this. So one thing we could do is like fold our either. If we fold our either, we've got two cases to deal with, right? We either have an L or we have an R. If it's the R case, we've got a value to apply to F. And doing so then is going to give us back an EitherT of F, comma, L, comma, S. So let's think about this. If we have an EitherT of F, comma, L, comma, S, what if we unwrapped that? Like an EitherT is just a wrapper, right? This is just a wrapper for F of either L, comma, S. And that's the exact type we need here. So on the right-hand side, it looks like we're set, right? On the right-hand side, all we got to do is just unwrap this, and we're good. We can unwrap it just by calling value. So we're good on the right, and we're done. Like, that's it. That's the whole function for the right-hand side, right? Because we're folding, so we're saying whatever E is, turn it into this. And now all we have to do is make the left-hand side also return something of this type. So let's just move that type up to here and get rid of this and say our function's done as soon as we can fill in line 14. Okay, so on line 14, let's think about the behavior we're trying to make occur. We have an L. We have like this L value here, a pure L value. And we need to somehow get this L value on the left side of an either and then wrap it in our F type constructor. So getting it on the left side of an either is easy. We can just use the left constructor, right? And now getting that inside of a type constructor is also easy. It just requires pure. And then we're done. And we've implemented our whole function. But let's now take a look. We've got two uses of methods for the type constructor F. We've got a call to pure. We've got a call to flat map. So we're going to need an implicit F here. And the question is, what type class do we need to implement this? If we only had flat map, we could have gotten it from the flat map type class. And we haven't talked about that much yet. That's coming up later. But it turns out there's a type class that only has flat map. But since we needed both flat map and pure, remember pure comes from applicative, the least or the least type class that has both flat map and pure is of course monad. So we need a monad instance for F. And all of that compiled fine. You can see that all worked. The only thing we're missing now is just like when we did the map example, down below, this isn't compiling because we don't have any evidence of a monad for F. Now, here we only asked for applicative because we were only using pure here. But since every monad is also an applicative, we can just change this to monad. Right? We don't need an additional argument. We can just change it to monad, and now we've got a working monad instance for EitherT. So in some ways, like this definition is not very interesting because it is very similar to the option T example. It's just a lot more complicated looking because we were carrying this left value all throughout. We've got an extra type parameter all throughout, right? So the point of kind of going through this exercise today with EitherT is to get experience with working with all of these extra type parameters and like being able to ignore them when we don't need them. We can just kind of like carry them along function to function to function and sort of like let the Scala compiler guide us into like what all parameters we need as we're building these things. I wanted to find one other utility function, not a type class on EitherT. But before we do that, let's do an example of using EitherT to make something simple that otherwise might be difficult. Okay, so let's go to SBT. All right, so I'm going to import structures. And we're going to import structures standard library support. And we're going to import our transformers. All right, so we got a bunch of things imported. Now let's say we have this list. All right, so we've got 3 writes in a list, 1, 2, and 3, and we're going to give it the explicit type of list either string comma int. Let's also define y's as a list of either string int. And we'll just give it 2 entries, 4 and 5. And so let's now try to use x's and y's in a for comprehension where we just want to sum, like we want to compute the cross product sum. So for a moment, let's just use, let's do a similar example using just list of integers. So for example, what we're trying to do is something like this. Right? So we've got list 1, 2, 3, we've got list 4, 5. We put it in a for comprehension and yield their sum. And we get back the pairwise sum, right, of every element. So we get like 1 plus 4, 1 plus 5, 2 plus 4, 2 plus 5, 3 plus 4, and 3 plus 5. Okay. So the question is that we basically want to do the same thing with our x's and y's here, but we want to bail out on the first left we encounter. So let's try just doing the same for comprehension with x's and y's. Seems reasonable enough, right? And you get some wacky error. And so like what's actually happening here is that like the for comprehension desugars, right, this first part, this first generator, this part here, desugars into a call x's.flatmap. It's going to desugar into this, right, x's.flatmap. And then we're going to have a parameter here called x. And then we've got some body. And then we're going to move on to the next generator. We see this y's generator here. That's going to get desugared into y's. And in this case, it's going to turn into a dot map. And we're going to get the y parameter bound. And then here we get our yield stuck in. Okay, so this is like the normal Scala for comprehension desugaring. And so let's look at our types. Remember, x's was a list of either string comma int. So we're calling flatmap on list, right? Flatmap on list is going to give us this variable here for each entry in the list, which means x has type either string comma int. Yet we were trying to treat it as an integer itself, right? And we end up with this really weird error talking about like found either string int required string for an even wackier reason, right? It's because anything has the plus method on it, right? Like anything you can call toString on and then concatenate. But like imagine doing the same example with subtraction, and you get a much different error. This time we get an error saying that like minus is not a member of either string int. At least that gives us a clue as to what's going on, that x is actually an either string int, not an int. Okay, so one way to do this would be to say, like, well, really what we're getting here is an x either. And really what we're getting with the y's is like a y either. And we could sort of try to maybe like nest our for comprehensions here And so now we're going to call like, we basically want to call flat map on x, but x isn't either, so you have to remember to pull the right projection out of the either. We could do the same thing here with the y either. You can do sums, for instance. Like we got the right answer that way by nesting, but like it's not even clear necessarily. That's a shame we lost that line. But it's not even clear that like the effects are occurring at the same time is really what we intended. Like we really want to say on the first x that we come across, there's no point in continuing through the y's. Maybe we got the same thing. Who knows? We'd have to like actually do all the math to figure out like how the flat maps and maps all unnest from each other. But like the general idea of like first break into the first level of things and then yield, the way associativity works here is you're yielding like a whole new expression, which is going to break into the next level of type constructors, right? And you're going to yield again. Like this sucks, right? And it's really difficult to reason about when you're seeing it in code. So once you get used to using transformers, we can rewrite this expression just as either t of x's and then y in either t of y's yield x plus 1. Right? And it just does all of that weird kind of nesting behavior for us. Of course, we get back an either t, and if we don't care to like continue to compose it with additional either t functions, we can just unwrap it by calling dot value, and we get back the same result. So like typically either t, this is exactly what you're doing. And rather than working with lists, let's say your functor type, the type constructor that you're working with, would be like a future, right? So now you can say like x's and y's are both futures that contain either an error message or a completed value. You can completely compose those futures in for comprehensions without having to worry about like unpacking those ethers at all, just by wrapping it in the either t type constructor. So it lets us kind of like forget temporarily about this bigger structure and just zoom into the value level and work with it in for comprehensions. Okay, so this is like the big win of EitherT in Scala, especially when you set that type constructor to future, or something equivalent, loosely equivalent to future. So like future of, my error type, comma, question mark. That's a very, very, very common one. If you're working with like Scala Z, maybe you're going to use task instead of future. That's another very common one, right? Okay, and that's like the big takeaway. Play with this and learn about EitherT in for comprehensions. But I want to do one more method that's fun.
Is there an easy way to say, like in that last example, suppose if I don't have any left types, I only want the list of the right types, not a list of either, and right 5, right 6. What if I just want the 5, 6, and 7? The values of values.
Yeah. So let's think about that.
I guess it would be like,
well, you want a list of the values.
I want a list of values, yeah. Or I guess I would want if there was a left type in there as an error handler or something, an error string or something like that. I would want that. Otherwise, I want just the list of values. That's normally what I think I would work.
Right. Let's go to the console. Just so I can get like a full big library. Let's do it this way. I want to just open up Scala Z so I have like a full functional library, not limited by what's just in structures right now. Because there's a couple different ways to do that depending on exactly what you want to occur. So we'll create, come on. SPT is never fast enough for me. Okay, here we go. So we're going to import all of Scala Z just to make it easy. And now what we're going to do is create our x's again as a list of, I'm going to use disjunctions. So we're going to say string or int. And this time, let's say we've got like 1.write, 2.write, error.left. And we'll say like 3.write. Okay. So there's this method. There's this method unite, which filters out the lefts.
Specifically filters out lefts?
No. So basically what it's doing, so unite comes from the MonadPlus type class, or in structures, it's the MonadCombine type class. Here's like the definition of unite. So remember, like MonadCombine is the type class that describes a type constructor that's both a monad and can give you a monoid for any f of whatever, right? So basically what it's saying is if you got one of these weird shapes, f of g, in our case, f was list and g was like either string or something, it can give you back just an f of a. So in our case, we're going to zoom past the left values and get just the ints, right? As long as g is foldable, and you know, in our case, our g was an either, and ethers are foldable. So basically, the way this works is it starts with well, so okay, let's actually look at it. We flat map over fg of a. We get a g of a as a result, and then we're going to fold over that g of a, saying start with just like the whatever g of a we have, and now for each a, lift it into our type constructor f, and combine all these f of a's together with a monoid. So f is a list. The monoid for list is just concatenation. Basically what we end up doing, the way fold works, is we're only going to be folding, like we're only going to get this function here called back for every write value. So we're just going to like walk through, because of the way fold map works, we're going to walk through all the write values, lifting every int into a singleton list of int, and then combine all those singleton lists together. So really, like what's causing like the lefts to be filtered out here is the fact that the foldable definition for either drops lefts and processes writes. So unite, you can use in a variety of ways, but that's a pretty neat one.
Yeah, I guess the case I'm picturing is one where, like I said, a left value is maybe an error value, and you want to know, do I have any errors? If not, just give me all the rights. That's kind of with this.
Yeah, so there's a couple other ones. Like, so this one would say just ignore all the error values. Right.
I'd also like to see why you're saying errors if they exist, otherwise give me all.
Yeah, so this one, sequence U, is like if you want to say break if any errors exist and give it to me. Yeah. Right. This would break when the first error. So that's that's let's call it error 2.left. Right, if we do sequence U again, it's still going to break on the first errors. That one's a little problematic depending on whether you want all errors or just the first. So typically, if you want all errors out, you would use a variant of sequence U. We can do it piecemeal, but basically what you would do is say, first, I want to map over each of my individual entries. These are all disjunctions, right? I'll call them E. And I want to turn these into validation objects. I think I could call it like that in Scala. Yeah. So I get back now like a validation string coming in instead of an either string in, right? And I'll talk about why in a minute. But the other thing I want to do is I want to convert the error message side into a non-empty list that contains one error message each, right? And I think I can do it like that. Yep. So now notice that like I get a success, success, then I get a failure of a non-empty list of error, right? And the same thing over there. All right, so finally now if I sequence U this, I get a non-empty list of error and error 2. And then because I typically only want to use validations while I'm doing these types of operations, I want to go back to a disjunction when I'm finished, and tacking that onto the end, we get back the left non-empty list. So anyway, the reason we had to go to validations in the middle of that is because like what's sequence U doing, right? It's you know, it's a little complicated. It's in that traverse type class. But like effectively, it's going to, you know, the disjunction, the traverse implementation for disjunction is going to error out, is going to halt processing, short circuit upon receiving the first left. Validation's traverse instance does not. It accumulates the values as it's traversing. And like neither are right or wrong. It turns out that like, you know, like you kind of have to have two different types to do it, you know, or at least different type class instances, because the behavior of traverse is tied up with the behavior of other methods as a part of the type class. So it gets a little complicated. And it's also,
I can see where they both have value.
Yeah. Absolutely. There's also a little bit of weirdness about, like you shouldn't, there's this concept called type class coherency, which basically says for any given type class, there should be like one canonical instance for your data type. So there should only be like one functor for list, one ever, you know? And like theoretically, you could provide two different traverse implementations for, and different applicative, different monad implementations for, I mean, really it's the applicative monad instance for disjunction, one of which is like this accumulation behavior and the other of which is not, you know, is just fail first. Typically it's considered sort of bad practice. But that's a very contentious thing that, you know, not everybody agrees with that. The other thing that I really like, okay, so remember X's is just this list of either's, right? So we showed how to get out just the good ones and filter out the bad ones. We showed how to get the first error. We showed how to get all errors. There's one other method that's very convenient. And what is the name of it? Oh man, it's not split, but basically it would give you two lists. The left list would give you all the lefts, and the right list would give you all the rights.
That's kind of what I was thinking about first. So
yeah. And I can't believe I'm blanking on the name of it. Yeah, and I am just totally blanking on it.
I know it exists.
Yeah, it does exist, and I'll post a link to it. Yeah, fair enough. Okay, so my very last method I want to show is just kind of a fun method, and this is going to be directly on EitherT. But now that we have this EitherT type, let's define this function. I'm going to call it plus plus plus. That happens to be what Scala Z calls it. And the idea is that we can, you know, sort of add two EitherTs together. So we're going to take, I'll call it other EitherT of f comma l comma r, and we can return an EitherT of f comma l comma r. And basically what I want to do is say, if we get like an f of left, it's sort of like an informal syntax, plus an f of right, I want to return the f of right. I want, like, just return this. And just swap the two. If I get like an f of right and an f of left. Oh, I'm sorry, I didn't mean that. I meant f of left here, right? Because we always want lefts to fail the computation. Okay, so anyway, if we get, and this is, you know, triple plus, that is. So I get an f of left and an f of right, I'm going to return just the left. Same thing there. But we've got two other cases to deal with. If I have like an f of left 1 plus f of left 2, I want to return, I want to like distribute this notion of adding inside something like this. And same thing for the right side. Something like that. That's the general idea. So we have a couple different ways to implement this. But rather than go through and derive this on the fly, I think it would be quicker. I just want to show the Scala Z implementation of this. And show just how it is implemented. Okay, so here's the Scala Z like pseudocode for this method that I was just showing. So the idea is if we get a right v1 plus a right v2, we're going to return a right of v1 added to v2. Right plus a left is always the left, right? Left plus a right is always the left. And then two lefts gives us a left of the sum. And so this is defined on EitherT. EitherT is a case class, and in this case, we call the other value, this right-hand side value on our operator is going to be called x. And the general idea here is that we're going to ask for an applicative instance for f. Now, this happens to be an apply instance for f. Apply is just applicative without pure. We don't need pure in this case, so we can avoid calling it. And this is actually going to be called map2, at least the way we're looking at these type classes, because that's the value. That's the map2 in structures and cats is the same as apply to from Scala Z. And just kind of aligning this with the code we had today, it would basically look like that. So we're going to say, let's just map directly over our f-type constructors to get inside to our raw values. And now we've just got two regular old disjunctions. And in this case, in Scala Z, disjunction defines this plus 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 method, which defines this exact behavior. If we go and look at that, oops, let's not do it that way. This is now plus 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 on just disjunction. Forget transformers completely. You can see it's just nested pattern matching, right? And it just defines the same table as above. It just says like if the left-hand side, right? And then it just goes all the way through and just uses semigroups to append the individual values. So if we get two lefts, then use the semigroup for our left type to append the two values. And if we get two rights, then use the semigroup for our right type. Sorry, I did that backwards. But two lefts, are done with here, and two rights are combined with this semigroup. So anyway, I think this is another interesting method because it's one that's very practical to use, and yet it's using a lot of these individual type classes we put together in very powerful ways to produce something that's very useful. So of course, an example of that would be like, well, we have x's. Let's create y's as just a list. And then we could do either t of x's plus 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 either t of y's. Now we're just getting those added together. So somewhere in here, there's like our first broken out left. This one, right? This is pairwise. Since we're using list, we're getting pairwise combination of these two lists. So for each error, you see like, error is combined with 1, error is combined with 2, and a left plus a right is always a left. So you get like 2 of the first error in the output, right? And you get 2 of the second error in the output. But otherwise, everything is just a right plus a right, in which case you just get their regular addition through the integer semigroup. So anyway, just another very interesting example, something to study of how to write these very, very powerful and yet completely parametric definitions. So anyway, that's all I have for today. Yes. Yeah, all that's just pure Scala Z there. Plus 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 does the reason I didn't want to derive this is one, we haven't written out. We would need a definition of plus 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 for either. And since we're using the standard library either, the standard library doesn't have a method like this because the standard library doesn't have semigroups. Structures doesn't define an alternative either type. I don't want structures to. Structures, I think, is more about learning the type classes. Cats does have something very similar to disjunction, but I think the name's going to change soon, so I don't really want to talk about like the cat's code yet until some of those names